Hello everyone. This video covers section 16 or section 16.1 and 16.2. The first topic is the central limit theorem, which is a review of probability, but is probably the most important theorem for what we had to do from now on. So the central limit theorem says the following. If you have a sequence of IID random variables, remember that IID means independent and identically distributed, where all of them have the same mean m and variance lambda square. So then if you define theta n to be epsilon 1 plus epsilon 2 and so forth all the way to n, then if you define theta hat of n to be equals to theta n minus n m divided by the square root of n times lambda square, that this has an approximately normal distribution where the mean is 0 and the standard deviation is 1. Obviously this is true as n goes to infinity. There is another way to write the central limit theorem, but for the purpose of this class, this is the most convenient one. Now recall from the last sections that z of n was defined as ln of Sn over Sn minus 1. Okay? And from here, the expected value with respect to the probability P of z of n was equals to mu delta t, and that the variance of Cn was equals to sigma square delta t, where remember t was equals to n delta t, and this is a fixed time. So therefore, if we define epsilon n to be equals to Zn minus mu delta t divided by sigma times delta t. So from here is easily check that the expected value with respect to P of epsilon n should be 0, and that the variance with respect to P of epsilon n is equals to 1. Also, more importantly, from here you can write or rewrite Cn to be equals to mu delta t plus sigma delta t times epsilon n. Right, now if you let theta n to be epsilon 1 plus epsilon 2 all the way to epsilon n, and we define theta hat n to be theta n over the square root of n, you can easily check, and you should check the expected value of theta hat n is the same thing as 1 over n, the expected value of epsilon 1 plus epsilon 2 all the way to epsilon n, which will be 1 over radical n times 0 plus 0 and so forth, which is just 0. n, that the variance of theta hat n is the same thing as 1 over radical n square times the variance of epsilon 1 plus the variance of epsilon 2 and so forth, all the way to the variance of epsilon n, okay, which will give you n over n, which is equals to 1. So therefore this implies the theta hat n by the central limit theorem, okay, by the central limit theorem, this has an approximately normal distribution or Gaussian distribution where the mean is 0 and the standard deviation is 1, or the variance is 1, as n goes to infinity. So this is very important. As the sample gets bigger and bigger, this becomes a standard normal distribution or a standard Gaussian distribution. Again, if you recall again from the last section, remember that the formula for S of n over S0, or the log of this, was equals to the sum from I equals to 1 to capital N of Ci. Remember that Sn over S0 was the same thing as S1 over S0 times S2 over S1 and so forth, all the way to S of n over S of n minus 1. This will be n, and this will cancel, so you end up with S of n over S0. Now in the last page we just come up with this formula that C of n is equals to mu delta t plus sigma times the square root of delta t times epsilon of n. Hence, if we plug in this formula in here, we end up with the sum from I equals to 1 to n of mu delta t plus sigma delta t epsilons of n. And notice that this one doesn't depend on I, so therefore this is just going to be n times mu delta t, and this will be plus sigma delta t times the sum from I equals to 1 to capital of N, it should be I, of epsilons of I. Remember that anything times 1 is equals to itself, so therefore here we're gonna multiply and divide by radical n, and the only reason why we do that is to get the following. So notice that this will be sigma delta t now times the square root of n times 1 over the square root of n times the sum from I to capital N of epsilon I. But by definition, also from the last page, remember this is what we call this part in yellow. This is what we define to be theta hat of n. And also remember that t is fixed and is defined to be delta t times n. So therefore, if you combine this and this, you combine this and this and this and this, you can simplify this to mu t plus sigma the square root of t times theta hat of n. Therefore, as n, capital N, approaches infinity, that means the ln of Sn over S0 is approximately normally distributed with mean mu t and variance sigma squared t, since this is approaching to a standard normal distribution as n goes to infinity. Therefore, this implies that the log return convergence, remember this is the log return convergence in distribution, okay, to a Gaussian or normal variable with mean mu t, mu capital T, and variance sigma square t, which again, remember, implies that Sn is equals to S0 e to the beta, where beta is a Gaussian distribution with mean mu t and variance sigma square t. And this result is going to be very important for the remaining of the class. Now we're going to try to derive the Black-Scholes formula in continuous time. We have done this actually in the discrete case. This formula is from chapter 10. We have used this before. So this is the discrete case. Remember the x was the fair price, and the fair price was defined to be the discounted expected value with respect to the risk-free measure. Remember that Q was the risk-free measure of the expected payoff. So we have done this before. So now the goal right now is going to be to get a formula like this, but in the continuous case. Remember that Q was called the martingale measure or the risk-free probability, and Q was defined to be like this. Remember we were using before the model that looked like this, which is the one we'll be using all along. And now here Q will be the probability that goes up, and 1 minus Q, it will be the probability that goes down. So again, the goal is going to be to derive a formula or a Black-Scholes formula for continuous time. Now Q was defined to be this, and in also, I believe it was in chapter 14, A was chosen to be of this form, mu delta t minus sigma the square root of delta t minus 1, and B, remember, was defined to be e to the mu delta t plus sigma the square root of delta t minus 1. If we plug these values into here and here, the algebra is pretty pretty messy, but this is a very good exercise to check. You'll end up with this. This will be e to the r delta t minus 1 plus a, which will be e to the mu delta t minus sigma delta t minus 1 divided by b minus a. You can see if you do b minus a, these two will cancel. So on the bottom, you'll end up with e to the mu delta t plus sigma radical delta t minus e to the mu delta t minus sigma the square root of delta t. Here these will cancel. So on the top you will have e to the r delta t minus e to the mu delta t minus sigma delta t. Then on the bottom you have e to the mu delta t times e to the sigma square root of delta t and then e to the minus sigma square root of delta t. The algebra is pretty messy, but it's a pretty good exercise, and you should definitely check what I'm gonna do right now. On the bottom, you can see that you can check factor e to the mu delta t. This will give you e to the sigma square root of delta t minus e to the minus sigma the square root of delta t. On the top, if we use the same trick from before, which will be to multiply by whole thing by 1, but here by 1 we're gonna use e to the minus mu delta t times e to the mu delta t, and you can see that you will be able to factor e to the mu delta t, and then if you combine this and this, you'll end up with e to the r minus mu delta t minus e to the minus sigma the square root of delta t, which you can easily see that these two will cancel. So therefore, we have the q can be written as e to the r minus mu delta t minus e to the sigma square root of delta t over e to the sigma radical delta t and so forth. Now, if you go all the way back to calculus 2, which I know it has been a long time, you remember e to the x, if you expand the entitled series, was equals to 1 plus x squared over 2 and so forth. And wherever you decide to stop, it will be the error. If x is relatively small, then you can say that e to the x is approximately equals to 1 plus x squared. We will not go farther than this, plus some error that depends on x, where this goes to 0 as x is getting smaller and smaller. Now, if you apply this formula in here, in here, in here, and in here, yeah, the algebra is pretty messy, so you have time, you should check it out. You will end up with r minus mu delta t. Now, if you subtract this from this, the ones will cancel. That's why there is no 1 on the top. And then this will give you plus sigma delta t minus sigma squared over 2 delta t plus the error to the 3/2. All you care is that this thing goes to 0 as delta t goes to 0. And in the bottom, if you do the same formula twice, you will end up with 2 sigma radical delta t plus again some error because you're not using the whole series, and this is approximately equals to 1/2, and this is sigma plus r minus mu minus sigma squared over 2 times the square root of delta t plus the error, and on the bottom this is just sigma plus the error. Remember that this goes to 0 as delta t goes to 0. Now if you do a little bit more of algebra, this will give you 1/2 1 minus the square root of delta t. This is mu plus sigma squared over 2 minus r divided by sigma plus big O of delta t. And similarly, you can find that 1 minus q is equals to this delta t mu plus sigma squared over 2 minus r divided by sigma plus 1 plus the error. Now, if we use these new probabilities and apply to this, remember that z of n was equals to ln of s of n over sn minus 1. So therefore, if we find the expected value, but now with respect to the new probability or the risk-free probability, the expected value of this is going to be r minus sigma squared over 2 delta t plus the error delta t to the 3/2. And this is a very important result, so you should check that this is true. This is a very good question to have on the test or the homework, but particularly for the next test. Also, the variance with respect to q of zn is going to be sigma squared delta t, again plus the error. Notice that the variance is practically the same as before, but the expected value under this new probability is quite different than before. You notice there is no value for mu at all here, which means this doesn't depend on the drift anymore. Hence, if we use this new probability and define epsilons of n again to be defined as zn minus the expected value but with respect to q of zn divided by the square root of the variance with respect to q of zn, that means that epsilon 1, epsilon 2, and so forth are IID, where the expected value with respect to q of epsilon n is equals to 0, and the variance with respect to q of epsilon n is equals to 1. this is epsilon 1. Okay, so then if we try this again, ln of Sn over S0 with this new definition, remember this is equals to the sum from I equals to 1 to n of Zi, which in this case is equals to the sum from 1 to n of, if you solve for Zn in here, this is going to be very similar to what we did before. This is going to be e to the cube Zn plus the variance with respect to q of Zn times epsilons of n. Therefore, this is going to be the sum of this, should be I, plus the variance with respect to q of Zi times epsilons of I, right? So the sum of all of this, which will give you the sum. You can break this into two sums plus this sum to n, the square root of the variance with respect to q of Ci times epsilons of I. So we already have this result. Remember that this one was equals to r minus sigma squared over 2 delta t, and then you have this n times plus the error n, and then this is delta t 3/2 plus the quantity that comes from here, which should be sigma the square root of delta t plus O of delta t times the sum from I equals to 1 to n of epsilons I. If we do the same trick and multiply this by the square root of n and divide by the square root of n, we get r minus sigma squared over 2. Remember, all of this is the same thing as just t plus bo of the square root of delta t. Notice that you multiply this by n, since t is equals to delta t n, that implies that n is equals to t divided by delta t. So you multiply this by that, you end up with just delta t to the 1/2, which is this part, plus, notice that if you multiply this times this, it's going to give you the square root of t. So this should be sigma times the square root of just t. And if you multiply this times that, that's going to change also the order. So it's going to be plus bo of the square root of delta t. And remember that this divided by this was equals to theta hat, this part. That's why we divide the square root of n. So that gives us theta, actually theta tildes of n. Remember that by definition this is equals to this, where thetas of n is a normal distribution that is standard. Now, since t is fixed, so we talked about this already, since t is fixed, by the central limit theorem, since this is a standard normal distribution, this implies as delta t goes to 0, the ln of Sn of S0 approaches to this distribution, sigma square over 2 t plus sigma the square root of t times theta theta tilde, where remember that theta tilde is approximately standard normal with 0, 1, or it has a normal distribution 0, 0, 1. Notice that saying that delta goes to 0 is the same thing as saying that capital N goes to infinity. So therefore this implies that ln of Sn over S0 approaches in distribution to theta, which is a normal distribution where the mean is r minus sigma squared over 2 t, and the variance is sigma squared t as n goes to 0, or you can say as delta t approaches, as n goes to infinity, or delta t goes to 0. Therefore, this implies that we end up with the same thing as before. The Sn is going to be equals to S0 e to the theta, where in this case theta is a normal distribution where the mean is r minus sigma squared divided by 2 times t, which is the expiration time, and then sigma squared times t. Notice, and this is very, very, very important. Okay, so notice the mu is missing, which means that the risk neutral probability in the limit doesn't depend on mu. Remember the mu was called the drift, and the drift is the real trend of what's going on with the stack. So this is very, very important, because if we are using the risk-free probabilities, this is now part of the picture. The distribution only depends on the interest rate and the volatility. So therefore, this gives us the Black-Scholes formula, which is what we were looking for. Black-Scholes formula. In continuous time, and the formula technically is this: x is going to be e to the minus r t e with respect to q of f of S0 e to the theta, where theta is equals to the normal distribution that we just found. So this is the famous Black-Scholes formula, and this is technically the price of European style options. And it is very important to notice that technically this is the same formula that we have in discrete time, which was almost identical, or x was equals to e to the minus r t, expected value of q of the payoff function S of n. But remember, in the discrete case, we were increasing everything by delta. So if we let delta t go to 0, we'll end up with the continuous formula. So you can see the similarity between the two. As we just showed, for European style options, the famous Black-Scholes formula formula is given by this: x is equals to e to the minus r t expected value f of s0 e to the theta, where theta was normal, r minus sigma squared over 2 times t, and then sigma squared t. Now, if we apply this to the basic European call, for the European call, the payoff was st minus k plus, then the price of the European is going to be e to the minus r t, the expected value with respect to q of the payoff function, which will be s0 e to the theta, where remember theta is this, minus k plus. So therefore, by definition, this is equals to e to the minus r t, expected value with respect to q of s0 e to the r minus sigma squared over 2t plus sigma square root of t theta tilde minus k whole thing plus, which is equals to expected value with respect to q of s0 e to the minus sigma squared over 2t. Notice that this part is going to cancel with this part, so that's why that disappeared, plus sigma, the square root of t theta tilde minus e to the minus r t times the strike price, the whole thing plus. Now the computations of to get this expected value is actually very messy. So for now, I'll just give you the answer. It's going to be equals to S0 phi of ln of S0 over k plus r plus sigma squared over 2t, everything divided by sigma square root of t minus k e to the minus r t phi of ln of s0 over k plus r minus sigma squared over 2 times t divided by sigma divided by square root of t. Notice how these two are almost the same, except that this is plus and this is This is minus. And here is very important that you understand what this function is. Phi of x represents the cumulative distribution function. So this is the cumulative distribution function of the standard normal distribution. So pretty much phi of x is the integral from minus infinity to x of e to the minus x squared over 2dx. Now to find this, you want to be able to integrate it, so you have to either use a table, a normal table, or a Gaussian table, or use a calculator like a TI-83 or 84. And again, it is very important to notice that to find the price of the European coal using the Black-Scholes formula, it doesn't require to know the drift or mu. It only requires the interest rate and the volatility, the expiration time, the strike price, and the initial value of the stock, which you know all of this. The only thing you have to be careful is that to compute this, you want to need a normal table or a calculator.